the universe, and I hope by the end of the lecture I would have convinced you that it is something exciting which is happening and something which you can think about as something to which you can contribute in the future. So, the plan of the lecture is as follows. I will begin with what I call as a primer on gravitational waves, and then talk about the discoveries and breakthroughs which happened in the first and second observational runs of the LIGO-Virgo network. The third observational run consolidated the picture which emerged in the first two. What is happening current now is called the fourth observational run. So, I will tell you the current status of the observations, and then where do we go from there, the fifth observational run, and then the plans for the next generation gravitational wave detectors, which is called the third generation gravitational wave detectors. While I go through this, I also at some particular point you know that there is something called LIGO India, a mega project where a gravitational wave detector is being built in India. So, I will basically tell you about what the status of LIGO India was when this was happening in the global scene. You have already heard the lecture on general relativity, and therefore you know that general relativity is Einstein's relativistic theory of gravity, and it is the epitome of what one can call mathematical elegance, conceptual depth, but the most important thing you have to keep in mind is the observational success which this theory enjoys. In Einstein's view, gravitation is synonymous with space-time geometry and mathematically described by the curvature or distortion of space-time. Einstein's equations are a system of 10 nonlinear partial differential equations. It is a rich system, mathematical system. So, even today, for example, mathematicians are interested in trying to understand the details of this equation. In English, this equation basically tells you that matter tells space-time how to curve, and in reaction the space-time tells matter how to move. Now, if you take any relativistic theory of gravitation like general theory of relativity, it must be consistent with the principle of special relativity. So, the effect of gravity cannot be transmitted faster than light. So, if a gravitational field of an object changes, these changes will propagate through space and take a finite time to reach other objects. This is what leads to the possibility of gravitational waves from Einstein's equations, just as we have electromagnetic waves emerging from Maxwell's equation. So, we can say gravitational waves are freely propagating oscillations of the gravitational field. If you ask in general relativity how does gravity manifest itself, it manifests as a tidal effect, and therefore, we can say gravitational waves are oscillating tidal gravitational fields which propagate out from the source. Now, if you examine the equations for gravitational waves in the general theory of relativity, a specific theory, then you find that the tidal force field is either oriented like a plus or like a cross. So, if this emerges and falls on a ring of particles, then the ring of particles would be tidally stretched and squeezed in an oscillatory time dependent manner. Therefore, if you want to detect gravitational waves, you should be able to measure the amount of squeeze which this system undergoes. And therefore, to quantify it, we define the notion of what we call gravitational wave strain. Now, how do I define gravitational wave strain? Take two test particles which are separated by a distance L, and if a gravitational wave signal passes through it and changes the separation by delta L, then take the ratio of delta L by L, and this is what is called as the gravity wave strain. So, if there is no gravitational wave, the strain is 0, but if there is a gravitational wave passing through this system, then it squeezes in one direction, expands in the other direction, and therefore, that ratio of the original, the squeeze upon the original length is what is called the gravity wave strain. From this simple formula, it is clear that if the strain is fixed, if the device is large, the displacement or the squeeze will be large. Now, the important point you have to keep in mind is Immediately after he gave the general theory of relativity, a year later, Einstein predicted that gravitational waves must be a consequence of general relativity using a simple form of his equation, which is called linearized gravity. You don't use the full nonlinear theory, but the linearized version of it. And then a couple of years later, he gave what we call as the quadrupole formula for gravitational radiation. So that basically says that the gravitational wave, like all waves, falls as 1 by r and is given by the second time derivative of the quadrupole moment. So that is the quadrupole formula. Now, if you have gravitational perturbations, that is what will determine the metric, and hence spatial separations and time intervals will be determined by the gravitational perturbation, and hence the strain on a system is really determined by the gravitational perturbation. So therefore, if you ask for the following question, how much is the gravity wave strain if you have a system of mass m moving with a velocity v, you will find that this formula reduces to this particular simple combination. So if you numerically evaluate it for a dumbbell consisting of 2 lorries, for example, separated by a couple of meters, rotating at about kilohertz, then the strain comes out to be 10 raised to minus 39. So this is a very, very small number, and Einstein therefore realized that it must have a practically vanishing value in all conceivable situations. Such ripples would be vanishingly small and nearly impossible to detect. And he was right. It almost took a century before we made the first detection of gravitational waves. So, to summarize, there is no experimental confirmation a la Hertz even till today. In a laboratory, you cannot create gravitational wave at one end of the lab and put a detector at the other end of the lab and detect it. And if you ask what is the fundamental reason between electromagnetism and gravitation, first thing is the gravitational interaction is weaker compared to the electromagnetic interaction by a very large factor, and also there is no dipole radiation. The leading order is quadrupole, and that is the reason if you try to convert mechanical energy to gravitational radiation, unless you have strong fields and relativistic velocities, you would not be able to create enough gravitational radiation. And the effect of gravitational wave on any potential detector would also be very feeble. So you cannot have lab sources. So the likely sources are signals which are produced by compact astrophysical systems where there are potentially huge masses accelerating very strongly. So though you can say that gravitational waves should exist in the laboratory, if you want to create gravitational waves, you really have to go to astrophysics. So this is one important point you have to keep in mind. Einstein predicted gravitational waves very early, but it was almost 40 to 50 years before a conceptual framework could say without ambiguity that gravitational waves exist in GR and what are the properties of those gravitational waves. So you can see that the theoretical understanding also took about 50 years. The basic question is, in general relativity, you can use any coordinate frame. So the whole question is, when you have gravitational waves, do they really transfer energy, or they are just an illusion because you are choosing coordinates which are wavy? So whether it's a gauge effect or whether it's a physical effect, this was the basic challenge and almost took 50 years to really get cleared. And this was really sorted out in a very famous meeting in Chapel Hill in 1957, and the 3 people who threw light on this was Pirani, who was a postdoc of Bondi, and Feynman. They basically finally argued that the tidal effect of gravitational waves is unambiguous, and therefore gravitational waves are also physical and they transfer energy. You can use gravitational waves to heat your water if you want, if you construct a suitable kind of system. Once this became clear, people could look for the presence of gravitational waves in the full theory, not just linearized gravity, and this was a big kind of progress which happened, and this was done by people like Bondi and his students, Chandrasekhar himself and his collaborators. In this meeting, Joe Weber and Wheeler were there, and after going back from this particular meeting, Weber decided that he will build a detector for gravitational waves, and this is the first detector which he built, which are called resonant bar detectors. You have a huge bar, and if a gravitational wave falls on it, it will set it into oscillation, and you try to modify, you try to sort of look at those oscillations by piezoelectric and convert it into a voltage which you try to sort of measure. Now, because this sort of resonates at a particular frequency, these detectors are narrowband detectors, and the kind of sources Weber thought would be important would be supernova. And he almost thought that he had, in 1969, he made a detection of gravitational waves, but people who tried to repeat that experiment could not find the gravitational waves. So, in a sense, we call Weber the tragic pioneer of this particular field. It was another 50 years before the final gravitational wave detection happened, and in the intervening 50 years, two important changes happened. From bar detectors, we went to laser interferometers to measure separations, and these kind of detectors, one can show, are broadband, they are sensitive over a range of frequencies. And in the astrophysics, some changes were happened. Jocelyn Bell, who was a graduate student like you, discovered pulsars, and a few years later, Hulse and Taylor discovered a binary pulsar. Now, the discovery of these astrophysical objects essentially showed that instead of supernova, coalescing compact binaries would be the kind of sources you can target for. And in this particular meeting, this was sort of really established, that the coalescing compact binaries are really good sources for gravitational waves. Basically, this is happening because you have a dumbbell made up of two neutron stars in the heaven. This is the 1974 discovery by these two gentlemen, Hulse and Taylor, of this object which we call the binary pulsar. And by the radio astronomy techniques of pulsar timing, you could reconstruct the orbit of this particular object and really show that something is happening in these interesting kind of systems. So, it was a watershed event because it demonstrated that because gravitational waves are emitted, the orbits will not be fixed, but it will be sort of inspiraling. And the observations were so sensitive that one could show that the gravitational waves are described exactly by Einstein's general theory of relativity, and these systems which would be coalescing compact binaries, these would be prototypical sources for the interferometer detectors which we will be able to build. So, the important point you have to keep in mind is that signal from a compact binary increases in frequency and amplitude, and finally it will plunge because of the non-existence of stable orbits, and then it will ring down. So, it is very elementary physics. You have two bodies, they are going around each other. So, you know what the frequency is by Kepler's laws. Now, when it comes closer, the frequency will change. So, that is the reason it is called a particular frequency, and the frequency keeps on increasing. The amplitude keeps increasing because the gravitational field is becoming stronger because they are coming closer to each other. So, therefore, this waveform is called a chirp waveform, amplitude and frequency increasing with time. I am just coming to that in a minute. So, it is sort of coming closer and closer. Then you may ask the question, if you have two bodies, why does something happen here? So, if you really look at the effective potential of this particular system, then you find that beyond a certain distance, you cannot have stable orbits. So, the system will sort of have to sort of plunge into each other. So, that is what is called the plunge phase, and then it will become one body, and then when it becomes one body, it is like a bell which is being hit, and when the bell is hit, you normally get a frequency, and that frequency dies off. That is what is called as the ring down of this particular black hole. So, a binary system comes together, merges and rings like a bell, and general theory of relativity is so good that you can calculate the frequencies of how much the frequency is and what is the ring down rate from the general theory of relativity. So you can predict something very, very accurately, and this plays an important role for what I will say a little later. So now we have a celestial dumbbell. We don't have to take 2 lorries and try to make a dumbbell. So if you take this binary system, now we know such systems exist. So they are typically of the mass of the sun. When they are almost about to plunge, their velocities are close to the velocity of light, and you put them in the nearest cluster of galaxies, which is the Virgo cluster, then the strain comes out to be 10 raised to minus 21. So from 10 raised to minus 39 for lab sources, you have gained 20 orders of magnitude. So this is the first important point you have to sort of keep in mind, that if you have a supernova, for example, you thought it is a very violent source, but it is not as, the strain from a supernova is not as large as this, and that is the reason supernova, though he was looking for it, it did not materialize as a source. So if you have a strain of this particular kind, you use your delta L by L formula and ask how much is the displacement. The displacement is about 10 raised to minus 18. If you convert it, it is about 1,000th of a Fermi. So it is smaller than a nuclear dimension. So even if you build a detector which is a kilometer long, you really have to measure something smaller than a nuclear dimension. And then if you want to detect gravitational waves, you really have to measure this very small quantity. Now to compare it with what is known historically, you all learn the Michelson-Morley experiment of special relativity, and if you ask what is the dimension it measures something of the order of nanometer. So you can see here, from Michelson-Morley experiment, you really have almost 10 orders of magnitude to be sort of gained. And if you say that every 10 years there is going to be an improvement of factor 10, it would take about 100 years to detect gravitational waves, and that's exactly what happened in some sense. So really a simple Michelson-Morley experiment doesn't really do. You really have to use everything which you know from laser theory and optics and so on. You have to have, for example, a Michelson interferometer with Fabry-Perot cavities, and then do power recycling, do signal recycling, etc. All these are advanced techniques which were known from laser physics. So if you hit it with all that, then you can go from this particular value to this particular value, which is what is sort of required. So physically what is really happening is, the laser interferometer is acting like a transducer. It's converting the gravitational wave to a photocurrent which is proportional to the strain amplitude. So the current would be proportional to the amplitude, and therefore you will be able to detect the strain which you want to do. So this is the order of magnitude of this particular quantity, but you realize that there are many other challenges to be overcome. Even if you build an interferometer and put it on the earth, it is going to be subjected to the seismic noise of the earth. And if you ask what is the order of the seismic noise, it's of the order of about a nanometer. So if you really want to measure something as small as this, you really will have to damp this nanometer motion by having a seismic isolation system. So again, that needed to be done. So you can see here that if you really try to look at that experiment, the experiment is a very, very challenging one, and basically involves laser physics, material science, seismic isolation. If you build a very large interferometer, again there should be no scattering inside the interferometer, so you need a very good vacuum system. And to control this particular system, you really need a lot of control theory. So all this almost basically took the 100 years to really develop, and that is therefore not surprising that only a few years before we made the first detection of gravitational waves. So as one of our colleagues basically said, every single technology they are touching, they are pushing, and there is a lot of technologies they are touching. So this really in a sense summarizes a one-line summary of the challenges of gravitational wave detection. Now assume that you have taken care of the gravitational wave detection part, the detector part. Then you look at the other challenges which come. Now if you look at the gravitational waves and look at the detector noise, you basically find that even from these powerful sources, the signal is buried in the noise of the detector. Other sources of noise will disturb the detector more than the signal will do. So you really will have to go and talk to your engineering colleagues, and they will tell you that this particular problem can be addressed if you use the technique called match filtering, where you try to do the following. You correlate a known signal, assume that the signal is known, correlate it with the data which you have, and do the ask how does the correlation look like. Then basically you see that at this point where there is no signal, you don't pick anything, but if the signal matches with something here, then you will pick up this correlation. So even though you cannot see this, you can see this, and this basically tells you that at this particular time in this particular data there is some particular signal. But then, just 1 minute, but then if you have to really pick the correlation and get its maximum benefit, you should be able to match your waveform as well as possible. If it does not match perfectly, the correlation will be smaller. So this basically is what you really have to do. That is what is called match filtering. But you don't know what the signal really is, because you don't know the parameters of this particular source. So you really have to create this waveform for all possible parameters which the waveform can depend on. So it will depend on the mass, it depends on the spin, and so on. So therefore, for every one of these particular parameters you have to create. So therefore, there is a big data analysis challenge, and also, as I said, you have to predict this waveform as accurately as possible. So your theory should also be as good as possible. And it turns out that the general theory of relativity is a good enough theory which can predict what the waveform should be. Somebody was asking you a question.
So how are we getting that known signal from the theory or?
Yes. So what is shown here is that there is an astrophysical signal which has come, and your detector, in the detector noise, it is sort of there. But since you will not be able to see this, you do this particular thing, this correlation. So therefore, you use your theory to guess what waveform would really look like. So that is what is called a template. So you create this particular template by using the best theory of gravity you have, and then for all possible parameters you try to create this bank and run this data which you have with all the templates which you have. So there is a very large computational overhead. So the computation which is available today is also plays a fundamental role in the search for gravitational waves.
So it is almost like model fitting.
What is that?
Model fitting, and we are fitting the.
Exactly. So, but in this particular case, even to detect it, you need the model. See, normally what we do is we detect something, and then from that detected thing we will say that our model predicts this particular waveform. So that is what I call the source characterization, which is what I show in the next slide, that the parameters on which your waveform depends are 15, because they depend on the mass of the system, the spin of the system, how far it is, how is it located in the sky, what is the relative orientation of the source and the detector, at what time does it coalesce, what is the phase at coalescence. So there are 15 parameters on which this waveform can really look like. So what you really have to do is basically use Bayesian statistical methods, that is, you create all possible things and try to ask what is the value for which this particular blue data really matches with. So I am sort of changing, for example, the distance, the total mass, and I will try to find out what is the best combination which will fit my theoretical model with. So this is how we basically say that my waveform represents this particular source with this particular mass, with this particular spin, located so far off from me. So your astronomy is basically done by first detecting it by using the theoretical model and then fitting the waveform to the best possible values which you can really have. So you can see here that the theory plays a very important role in this particular exercise. And if you really ask what was the history of gravitational wave research in India, essentially the LIGO detectors were sort of planned in the early 90s and so on, and at that particular time in India for about a couple of decades there was work on source modeling in RRI in a group around me in collaboration with my French colleagues, and there was work on gravity wave data analysis, how to construct templates, how to construct a template bank. This was work in IUCAA around my distinguished colleague Sanjeev Dhurandhar. So this essentially was the research happening in India in gravitational waves for almost a couple of decades. Now, what was happening at the experimental end? The LIGO detector was being built in the US, and they basically realized that since you are measuring something very, very small, you will be dominated by effects of the environment on these particular detectors. So to be sure that you are detecting something astrophysical, it would be safer if you had two detectors and you saw the same signal in both the detectors with the difference in time which it takes for gravitational waves to move from one point to the other, or depending on how far it is from the source, the projection effect. So there is there was a site in Hanford, there was a site in Louisiana, but then they wanted to be even more careful. So basically had two sites as far away in the US as possible, and in one of the sites in Hanford, in the same beam tube, they put two detectors. So therefore they had two sites and three detectors. And this is really important, because if you really ask, how can I really know that my gravitational wave is coming from a source from a particular direction? Now, if you really had only the output of a gravitational wave single detector, the antenna pattern is very, very symmetric. So that means in whichever direction the gravity wave comes, the strain value is not very, very different. So you really need a network of detectors, and that is the reason the Europeans built their own detector, which is called Virgo, at a place near Pisa, which is called Cassina, a detector which is slightly smaller, 3 kilometer long detector. And if you had three detectors, then as the police do when they want to locate from which mobile a signal is coming, you try to look at different towers from which that signal is coming, and then if you do triangulation, you can basically try to locate where the source is. So that is exactly what you really need to do. You really require a global network of gravity wave detectors, because given a particular detector, the source can lie on a sphere around it, depending on when it comes. If you have one more detector, there will be one more sphere, and if you have the third detector, you will have one more sphere, and by looking at the common points to all these three things, you will be able to locate where the source is. So you need a network of detectors if you really want to locate a particular source. So people, when the first LIGO initial phase of LIGO was done, people try to look for the astrophysical question that if we really look at the two Hanford detectors, the Livingston detector and the Virgo detector, how does the source localization look like? Then they basically, when they did the simulation, they basically found that sources here could be localized very well, but sources here are not very well localizable. So we really don't know, the gravitational wave could have come from here or could have come from here. So the localization is poor in this particular region, which is close to the plane of this particular network. So then the question was, let's take the second detector here and move it to a place in Australia or in India or something like that. This diagram becomes like this. So you basically realize that having a LIGO detector which is as far away from the American detectors as possible really allows you to do astrophysics much better. And therefore, instead of keeping the same detector in the Hanford beam tube, they basically explored a collaboration with India, and that is what we call the LIGO India project, that the Americans will provide the detector which will be installed in an infrastructure in India, and that will allow you to do astrophysics which is much better than the astrophysics possible if the detector remained in the US. And later on, when this was sort of basically studied by these colleagues when we proposed this particular project, and later on the science case of LIGO India has been investigated, and in this particular article you will find the advantages if the detector like LIGO India exists in this particular network. So this is what I was basically telling you, that I will tell you what was happening in the LIGO India project at the time something was happening in the US. So in 2009 a consortium was formed in India which was called the Indigo Consortium, and its mandate was, the idea was that we have a community doing source modeling and data analysis, but maybe now is the time to really plan for a gravity wave experiment and participate in the data analysis happening in the LIGO scientific collaboration. So this was the mandate of the Indigo Consortium, and therefore when the opportunity emerged in 2011 we made the LIGO India proposal, and the Indigo Consortium became a member of the LIGO scientific collaboration. What that means is, whenever LIGO takes data, that data is accessible to us and we can do the science which is possible even though we don't have our own detector. So that is the LIGO scientific collaboration. Now I told you that we understand that gravitational waves are physical, so we look at Einstein's equations and from that try to ask the questions, what are the properties of gravitational waves, like we have properties of electromagnetic waves. And then we find that if you have a general theory of relativity, just as it happens in electromagnetism, the gravitational waves, the speed is the speed of light. The waves are not longitudinal but they are transverse, and the states have two states of polarization. Remember, in the gravitational, in the electromagnetic caves, we have linear polarizations. If the electromagnetic wave travels in the z direction, you can have oscillations in the x direction and the y direction. Here I told you that the tidal fields are of two kinds, and because the tidal fields are of two kinds, that is what leads you to the two states of polarization in the case of gravitational waves. Electromagnetism, in the electromagnetic case there is dipole radiation, but in the case of gravity there is no monopole or dipole radiation. And if you ask, is there a fundamental reason for that? The answer is yes, there is a fundamental reason, because there are conservation laws of energy, linear and angular momentum, and these conservation laws prevent the possibility of monopole radiation and dipole radiation. For example, in electromagnetism you can ask the question, why is there leading order dipole and there is no monopole radiation? Precisely because charge is conserved. Charge is the analog of mass in this energy, and therefore because of the existence of conservation laws there are no lower order radiation. Eh, Yeah, so what I said was just look at the electromagnetic case. In the electromagnetic case, you understand if the wave propagates in the z direction, the two states of polarization are the oscillation of the electric field in the y direction and the x direction, right? So in the case of the gravity, I told you that the physical aspects of gravity are tidal aspects. And then if you ask how many independent tidal fields are there coming from Einstein's equation, it turns out there are two independent states of tidal polarization. So because of those two states, independent states of tidal polarization, you basically have the two states of polarizations in the case of gravity also.
So why do these gravitational waves have to travel at speed of light?
Why they have to travel at the speed of light is related to the fact that if you had a quantum picture of gravity, it is transmitted by gravitons which are massless. And from general field theory, one can show that if the carrier is a massless thing, then the speed of propagation will be infinite. So there is a fundamental reason why.
Yeah, that is because of information cannot travel
More than speed of light.
But the information which is generated by the impact of larger objects,
Yes.
how does it equal to the transition of an electron?
No,
It's like the information which is generated by some quantum.
the bodies are moving at some finite speed, but the radiation is a different thing. It is no,
No,
the radiative fields.
I'm not asking about that thing, but I'm asking about that how can some information which can travel at speed of light at quantum levels have the same impact which is created by an transition of electron?
No, because it's related to the masslessness of the carrier. When you write down your field, when you do field theory, then you ask the question, what mediates the force field which you are looking at? So that turns out to be, if for example you look at electromagnetism, it's a photon and the photon is massless. If the photon had mass, for example, then the speed of electromagnetic waves would not be the speed of light.
Yeah, but the impact which is made by celestial objects, does it equals to transition of electron from higher orbit to lower orbit? Because they are generating.
If there is, so as I said, if you have a quantum picture, there is no quantum picture for the case of gravitational case. So you really cannot have the Bohr picture. But if finally there is a gravitational quantum theory of gravity, then exactly as we are sort of saying in the electromagnetic case, in the case of atoms, what we talk, that same thing would be applicable even for the gravity case. So the important point is that if you have a system, it will lose energy, angular momentum and linear momentum. And just as charged particles, accelerated particle charges create a dipole radiation, accelerated masses create gravitational radiation. So that is sort of very similar to what happened in electromagnetism. But there are differences, and that is what makes it interesting, because of the fact that the interaction of gravity with matter is 10 raised to 39 times weaker. So therefore, you will be able to look for gravitational waves from the heart of a supernova, because the gravitational waves would interact very weakly with all the matter which is there on the way. Whereas if you had the electromagnetic radiation from the heart of a supernova, it will be scattered so much that you would not be able to locate what is happening to the electromagnetic wave from a supernova. And therefore, if you take it to the early universe, we really know that the early universe, there is a cosmic microwave background radiation. So it comes from a particular epoch in the life of the universe. But if you had the gravitational waves created from the Big Bang, you would be able to see it almost when the universe was getting created. This is basically only related to the fact that the coupling constant of gravity related to electromagnetism is very, very small. Lastly, I told you that the properties of gravitational waves, which I showed you in the previous slide, comes from the general theory of relativity. So therefore, if the general theory of relativity is not the correct theory of gravity, and you look at a different theory of gravity, like gravity transmitted by a massive graviton and so on, then the properties will be sort of different. Therefore, finally, you will be able to test the general theory of relativity by measuring the properties of gravitational waves itself. So you can see how the whole thing goes in a kind of cycle. You begin with gravitational waves from general theory of relativity. You predict the properties of gravitational waves from the general theory of relativity. To detect the gravitational waves, you need the general theory of relativity. You get astrophysics by using the parameters and determine it from the general theory of relativity. But finally, you go and test that same theory, because if the properties of gravitational waves doesn't match with what you are seeing, then it means that there is a correction to Einstein's theory of relativity, and that will be the better theory of gravity in the future. The last thing I want to say in my primer is the kind of objects which we are talking about are binary neutron stars, because that is the kind of object which we had seen. But then you may imagine that in addition to binary objects, if the mass of the system is larger, they would not be a neutron star, it would be a black hole. And you can imagine a binary black hole kind of system. So when people were talking about coalescing compact binaries, they knew that not only there are binary neutron stars, there can be binary black holes, and there can also be, what is the time? The time is right? Okay. I suddenly thought I was relativistic and I was sort of damned, and my time had run out. So you had binary neutron stars, binary black holes, or imagine a system made up of one neutron star and one black hole. So theoretically all these things are sort of possible. Now the idea of a black hole is something which does not have structure. It's almost like a idealized point particle. So when you use Einstein's equations and ask for how does the waveform look like, it is like the waveform from two point particles going around each other. But then the important point you have to keep in mind is that this waveform is like a ECG. If there are other effects, for example, if it is spinning, two black holes are spinning from each other, then it will affect the waveform. There is something called backscatter, which is called tail effects, that will affect this particular waveform. In the case of black holes, there are horizons, and the horizon absorbs radiation. So black hole absorption will cause effect on this particular waveform. And then, as I told you, Vishweshwara, who used to be in this particular institute, he was the first person who predicted the existence of quasi-normal modes, that if you have a black hole and the black hole rings down, it will create these quasi-normal modes. So in your data, you will be able to look for signatures of all these particular things. But now suppose you had a neutron star instead of a black hole, then what will happen? Now the black hole is, as I told you, very, very rigid, it is like a point object, but a neutron star is made up of ordinary matter. So when two neutron stars come close to each other, one system will start affecting the other and tidally start distorting it. So the waveform will start deviating from the point particle approximation, and how much it will deviate will depend on how much tidal distortion will happen. But what decides the tidal distortion? It will really depend on the properties of the which determine the interior of this particular neutron star. So that is determined by microphysics, the neutron star equation of state. So from an astrophysical observation of how the waveform deviates from the point particle approximation, you will be able to estimate the tidal distortion, and from the tidal distortion you will be able to determine what all equations of state are consistent with that tidal thing. So you will be able to extract microphysics from an astrophysical observation. So that essentially completes my black hole primer. So if you really look at papers which are there in research, you will find that one of these particular slides will be relevant to what is discussed in that particular paper.
Recent developments in attosecond physics.
Yes. Let's talk about human intelligence first before we talk about us.
So my question was like, these interferometers depends upon time delayed systems, right?
Correct.
So if we can use this attosecond.
Absolutely. Even today, now instead of my lecture, we could have it by AI, right? So the question is, I think, this question, everything which we are doing by standard data analysis techniques, AI and machine learning, people are trying to improve whatever is happening by these particular techniques. So that's a very rich emerging research field which has already become very hot. Can you just speak up? I have a little problem with hearing.
How can we explain the gravitation of a wave energy density? Like there,
No, I didn't.
intrinsically nonlinear since the wave energy density itself gravitates.
Yeah. So the point is that since once you have these particular equation, the nonlinearities can be calculated from the theory itself, and you can calculate the effect of the nonlinearities on the particular waveform by extending the techniques which you have for calculating the linear effect. So it is exactly like we learn in quantum mechanics perturbation theory. So you begin with the linearized solution, then you use the linearized solution and make it the source for the next order, then calculate the first order correction and then the second order. So what you really have to do is use the full Einstein's equations, and just as you calculate the lamp shift in electrodynamics, you do the same thing for calculating the waveform. So that's how all the waveforms which are being used are calculated, and therefore every time you calculate a particular order, it takes about 10 to 20 years to go from one order to another. So this is the primer, and now I basically go to what are the results which have been obtained. And as I just told you, the first observational run involved only the LIGO detectors, and as I told you, the initial detectors didn't detect anything. The second generation detectors, which are called advanced detectors, they made the first detection. The second observational run involved both the LIGO and the Virgo detectors. This is the funding agency, the National Science Foundation, which funds the LIGO laboratory, and therefore I have to sort of point out that it supported the building of the advanced detector. So the first observational run of the advanced detector began on September 12th and lasted for about 4 months, and just a few days after that, immediately you switched on, and on 14th September, we saw in the LIGO detector at Hanford and Livingston a telltale signal, a signal which looked very similar here. When you look more in detail, the waveform here and the waveform here looked very similar. There was a slight shift because, as I told you, they are at different places. So if you shift it by the 7 millisecond, then the waveforms match very well. So this is what I basically said, that you are sure about it because two detectors which are very far away see the same signal. So it cannot be created by some instrumentation artifact. Then, as I told you, we know how to solve Einstein's equations numerically. So because from this particular exercise, I told you that you can determine the parameters of this particular system. So, using those particular parameters, you theoretically calculate what Einstein's theory predicts, and this is what is shown here, the numerical relativity calculation for that particular thing. And then again we show that the waveform and what you theoretically calculate, there is no difference between them. The residuals are consistent with the noise. So, this is the first direct detection of gravitational waves, almost 100 years after the general theory of relativity was given, and just 3 days after the instrument was sort of switched on. But the important point you have to keep in mind is that this first discovery already had astrophysical implications. It is the first direct detection of gravitational waves, as I explained. The gravitational, because you know the parameters of the system, one can say that it has come from a binary black hole system, and you could determine the distance. It is at a cosmological distance of about 410 megaparsec. This was the first detection of a binary black hole, and it is merging within the age of the universe, because that is why you have been able to sort of see it. The masses of the individual systems was larger than about 25 solar masses. Now, when you have a system with this high mass, you have to ask what are the astrophysical conditions in which such bodies can be made. So, it says something about the environment of this star, and it basically says that the winds cannot be very large, because if the winds are large, the mass would be sort of smaller. So, it says that there was a time in our cosmic history when there was weak star winds. Weak star winds implies that the metallicity of the medium was sort of smaller. So, you can see here, just from the detection of this particular system, you are extracting astrophysical information. And then, as I told you, you can look at the data and try to confront it with the predictions of general theory of relativity. And because this is being emitted when the gravitational field, when the system is sort of about to sort of inspiral and merge, it is a regime where the gravitational field is very strong. So, this is a test of general theory of relativity in the strong field regime. So, again, to come back to the LIGO India story, because of the fact that we were part of the LIGO scientific collaboration from 2011, in this discovery paper which got the Nobel Prize, there were 37 authors from Indian institutions, and in the paper you would see citations to important papers written by these two groups. The more important thing was, even though we had made a proposal in 2011, even till 2016 the project was not approved. But the moment the gravity wave detection was really made, in 1 week the approval for the LIGO India project, what is called as the in principle approval, was really achieved. So, it is very, very strange that something which happened at a cosmological distance affected something which happened in India. So, as I said, if you believe in astrology, you have to take into account also the binary black holes which exist in the universe, because if the binary black hole detection didn't happen, I am not sure whether the LIGO India project would be funded in that particular year. So, we live in an imperfect world, and we have to keep that in mind. These are the institutions which are the lead institutions for the LIGO India project. Immediately, because of the detection, the people who were involved in this particular project, Barry Barish, Kip Thorne and Rainer Weiss, they got the Nobel Prize in 2017, and the citation basically said, for decisive contributions to the LIGO detector and the observation of gravitational waves. The thing was an experimental success, and therefore the experimenter in the project, Ray Weiss, got half the Nobel Prize. Quarter of them was given to Kip Thorne and other quarter to Barry Barish. He was the theoretician behind many of these things and also involved in the experimental part. Barry Barish was the person who brought into the project techniques like having a very large collaboration, a kind of paradigm which the high energy physics people use. So he was basically a high energy physicist, and he basically argued that LIGO, the gravitational wave detection, is a major project. It cannot be done by small laboratories. There should be a larger collaboration looking at various aspects of that particular project. So for bringing in that particular aspect, he also shared the Nobel Prize. The second observational run began in 2016, and in the beginning Virgo could not join, but almost in the last month on 1st August Virgo joined. And again a couple of weeks later the first black hole by 3 detectors were really sort of seen. The LIGO detectors, and very weakly, because the Virgo detector is not very sensitive, so it did not see the signal as prominently as possible. But even then, because we had 3 detectors, you could localize the sources much better. If you had only 2 detectors, the sky localization would be over 1000 degrees. Because of the Virgo detector, the sky localization became 60 square degrees. Why is this important? Because once you know the sky localization, you can point your other telescopes through that particular region and see, for example, whether electromagnetic radiation is coming from that region in the sky. If this region in the sky is very large, then the locating the electromagnetic counterpart is not very. And this indeed played an important role, because just a few days later we saw the first detection of gravitational wave from a binary neutron star. And this was really something spectacular. So what is shown here, for example, is the gravitational waveform. Again, it was detected by using the match filter idea. It used the models which we had all calculated, me and my French colleagues had sort of calculated, and you saw that it lasted for a long time. So we see the early in spiral and then the ramping up where it sort of merges. But what is important is that at the same time a Fermi detector saw something which was a gamma ray burst. So in a sense we are seeing exactly the birth of a multi-messenger astronomy. There is a source which put out gravitational waves, and looks like at the same time a source from that same source a gamma ray burst is coming. But because you could locate the source in the sky, we could pass on this information to our astronomy colleagues, and they could basically detect other electromagnetic radiation from this particular region. So once again, but then the important point you have to ask is, the universe is so large, it could just be a statistical fluctuation that something from some object and something from some other object really came at the same time. So the only way you can be sure is if you can make sure that they are coming from the same region in the sky. And that is the reason for which you need the sky localization information. So the moment we had the sky localization information, we passed it on to our astronomy colleagues, and in about 12 hours they could locate the galaxy from which the electromagnetic radiation should be sort of basically coming. So this was the first observation of gravitational wave from a neutron star system, first observation of gravitational waves and electromagnetic waves from a single source. It supports the hypothesis that this system was produced by the merger of two neutron stars in a particular galaxy. It was followed by a gamma ray burst, and then there was something called a kilonova, which is powered by the radioactive decay of R process nuclei synthesized by the nucleus. So, you can see very much detailed information is being obtained about that particular region in the sky. A gamma ray burst, a kilonova, the nucleus involved in those particular ejecta and so on. And as I told you, because it is a neutron star, we can put estimates of the tidal deformability, and therefore you can say something about the equation of state. So, all this really happened, and as far as I can say, at some particular point this object should get a Nobel Prize because of all the things which it basically did. It was to me a very interesting point that we take take for granted that gold, platinum, uranium should all be there. But if you really ask how can you make them, even today, for example, when this particular object was discovered, people really didn't know how you really make these particular objects. There was a general feeling that supernova should create them. But then the supernova are so rare that you really cannot explain the abundance of these particular metals. But if you really believe in the neutron star case, this R process, these are neutron stars, so there is a very large number of neutrons, and the R process can really create these kind of objects. The reason this is a very interesting object is, since its discovery, more than 2000 papers has been written which refer to this particular object. All kinds of aspects about the jet which comes from there, the model for that jet, details of the R process, details of the afterglow, the fact that this kilonova is very spherically symmetric. So, follow up of this particular object happens, and therefore in a sense it has created a multi-messenger time domain astronomy has really emerged from this particular object. And therefore it is clear that in the future gravitational wave, electromagnetic and neutrino observations should really be done jointly. I am just having a problem with my legs, so I will just sit down, if you excuse me. You can do cosmology by this particular object because of the fact that by gravitational wave observation you can measure the distance of this particular source. I told you that electromagnetic radiation is coming from the same source, so you can measure the redshift of this particular source, and by taking the ratio of the redshift and the distance you can calculate the Hubble constant. So, once you have an object from which electromagnetic and gravitational wave radiation are there, you can do cosmology, and this is an independent way of determining the Hubble constant. As you know, there is today the problem which is called the Hubble tension, because determining Hubble constant from the supernova and from the Planck data give two different values. So, in the future we are hoping that this produces an independent way of determining the Hubble constant, which will try to break the problem which is there in the determination of the Hubble constant. You can test the general theory of relativity by using this particular object. I do not want to read everything, but there are many predictions of the general theory of relativity for the data, and all of them can be tested. And there was a physical review letter which basically talked about the consistency of the data and how good is the data with the general theory of relativity. So, this is what I was basically saying, that whenever you test the Einstein's theory of relativity, till today all observations are very consistent with the general theory of relativity. So, now let us look at what it tells us about the universe. Before gravity wave observations detection, we knew that there are neutron stars by electromagnetic observations, which is shown here. And because of X-ray observations, you can talk about the black holes which are seen by electromagnetic observations. They are sort of shown here. But when the gravity wave systems were seen, they led to black holes which were more massive. So we have seen something which the electromagnetic observations could not see. And as I told you, there is also the gravity wave from the binary neutron star that was also sort of seen. So we are seeing something which electromagnetic observations could never reveal, because of the fact that the electromagnetic radiation from black holes, even today it is not clear whether anything will be there from binary black holes or not. Black holes are like giant vacuum cleaners. They seem to take away all the matter and all the radiation, and therefore it is an important question whether in the future we will see electromagnetic radiation from binary black holes or not. So in the third observational run, as I said, this picture which emerged was consolidated. There were, the way we do our observation is we observe for a certain amount of time, take down, stop the observation run, improve the detector, and then again look for the gravitational wave from that. So that is the reason you will see that there was a month in between where the detector was tuned further. So every time an observational run is broken up into parts, where the sensitivity in the later part is supposed to be better than in the previous part. In the third observational run, we did something more ambitious. In the previous two runs, we only shared our information with colleagues with whom we signed MOU. In the third observational run, we decided that we will release openly the data, so anybody who wanted to look for electromagnetic radiation from our gravitational wave sources, they would be able to do that. So this is what is called low latency alerts, and the alerts were public. So you can see here, the moment you see look at the data and see some particular event, a preliminary alert is sort of sent. It's almost sent before a minute is done. So we should be able to do all our gravity wave detection and parameter estimation very, very fast. And that is where your question becomes important, whether by using AI and machine learning, this can be made even smaller than 1 minute. And that is what people are trying to do now.
It's not about AI machine learning, it's about attosecond physics.
What is that?
Attosecond physics, 10 to the power of minus 18 or so.
No, that is different. This is I am talking about the processes, how fast you can sort of do that.
So what happens is, if we have to measure gravitational waves using LIGO, either if we have to get like stronger signal, the length of the observatory should be longer.
Yes, that is a different question.
Or the measurement is to be
But
shorter.
no, that is a different question. But what I am talking about is the statement about alerts. That the alert giving can be improved by improving the data analysis techniques. And therefore, after the preliminary alert, humans have to look at the data, whether the alert was due to gravitational wave or whether it was due to some instrumentation glitch. So either you retract the alert or you confirm and give more details about the alert. And then you do a more rigorous classification and get the parameter estimation, and finally in a week's time you have more rigorous information about the whole thing. So this was attempted in the third observational run, and at the end of the third observational run we had 90 gravity wave events. That is basically shown here. What is shown here are different systems, their masses. These are the two binary systems, the component systems which creates that particular thing, That is what is shown here. And if you really ask what does this catalog basically have, for example, we saw the second binary neutron star. We saw a neutron star black hole system. We saw a intermediate black hole intermediate mass black hole system, which is 150 solar masses at the top. We found systems which are asymmetric. So you can see, as we start probing the astrophysical system, the populations have very, very rich kind of properties, and therefore in the waveform we can try to look for signatures of spin, of eccentricity and other aspects in this particular data. And this is what is really happening. Because we have seen about 90 systems, we can make a guess for what is the rates of these particular objects. For example, our current estimate is that binary black holes per gigaparsec cube per year should lie in this particular range. For neutron star, it should lie in this particular range, and for neutron star black hole, it should lie in this particular range. So, if your detector becomes more sensitive, it can see further, so you will see more events, and therefore this is exactly what we sort of look for when we go to the next generation, next observational run. And then if you look at the literature, you would basically see that the gravity wave data is used for all these kinds of research projects. As I told you, you send out an open alert and then look for electromagnetic and neutrino counterpart. That is one thing which we do. We try to identify events which are exceptional, which have different properties compared to the previous one. We create a catalog of these, and in this catalog the parameter values of this particular system are given. I showed you the rates of these particular objects, and then we start looking at the population properties. Is there a paradigm? Is there a kind of pattern in these populations? Are there formation channels which are consistent with this population, and so on. Then I told you that we test general theory of relativity, we do cosmology. In electromagnetic astronomy, there is something called lensing of electromagnetic waves. Similarly, gravitational waves can be lensed. We look for signatures of gravitational wave lensing. And in addition to these coalescing compact binaries, we look for other kind of sources, supernova sources, which will be burst sources, gravitational waves from fast radio bursts. If you have a pulsar, from that there can be a gravitational wave. These are called persistent sources, and whether there is some exotic sources which we don't know anything about. So all these things are done with the data. So to end my last part, we are currently in the 4th observational run. Again, as I told you, the observational run in the first involved only LIGO, in the second run it involved Virgo, and maybe in the third observational run it will also involve the Japanese detector, which is called the Kagra detector. Our alerts now are done more sharply, we can do it even faster, and therefore our alert program has become more sophisticated than before. And now we basically see that indeed, because our detector is more sensitive, we are seeing more kind of sources. So at the end of the third observational run, we had seen 90 transient sources, but today at the end of the 4th observational run, in the middle of that, we have seen 293 sources in all. So more than 200 sources have been seen in the 4th observational run. We used to send alerts only for significant sources. Now even for non-significant sources which have low significance, we send out alerts. And some of our electromagnetic colleagues look for gravitational waves from these kind of sources, because we really don't know what gravity wave strength corresponds to an electromagnetic counterpart. So this is what I showed you, that we have burst sources. This is the coalescing compact binaries. This is gravitational waves from pulsars, gravitational wave from burst sources, and if you can't resolve these sources, they will all combine together and create a stochastic background. So we look for the stochastic background from the early universe and from astrophysical combinations. What is shown here is that in this particular paper we have put a limit on how much is the strain sensitivity of continuous waves from known pulsars. There was a supernova event which happened quite close to the Earth, and again we look for gravitational waves from this particular, we couldn't find it, so we could put a limit on what is the strength of gravitational waves from this supernova event. So you can see here that there is quite a lot of activity which happens once the data is taken. The story doesn't end there. We are in the 4th observing run. What will happen now is by the end of October this will stop and we will start installing important components to our detectors, so that in 2027 the 5th observation run will begin. You can see here, today we can see up to 160 megaparsec. When the detector becomes more sensitive, we will be able to see as far as 325 megaparsec. So with this particular thing, in the earlier runs we could see one event in 5 days. Now we see about one event in 3 days. In this particular era we will see 3 events per day. So it is going to be an era where we will be inundated by events. And what is the status of LIGO India during this? The LIGO India project has found a site in a place in Maharashtra called Aund. This site has been completely obtained. The vacuum system has been prototyped by the Plasma Research Institute. A facility to do a prototype is being built at Raja Ramana Center for Advanced Technology in Indore, and at IUCA, outreach, human resource development, computing, multi-messenger astronomy related work is really happening. So from 2016 when we were approved till today, all this prototyping work and site acquisition has happened. So now what we used to call Indigo has become what is called as the LIGO India Scientific Collaboration. So in 2019, Indigo transformed itself into LIGO India Scientific Collaboration because we wanted to have an integrated community for the detector and for the science. We are very happy that in 2023 the full approval, remember in 2016 we got the in principle approval, the funding had not happened. The full approval happened in 2023, and just in 2025 the tender for the civil and vacuum has really gone out. So in a few months the tender will be sort of given to some particular agency, and the construction of the LIGO India project observatory will really sort of begin. It is anticipated that when all this work is done, by 2030 the detector will be ready to take data in the Aunda observatory. What is important for you to keep in mind is that the fact that LIGO India will be available is important, because even when you have the 3rd generation detector after 05, multi-messenger astronomy will be facilitated by the existence of LIGO India. Just recently there was a paper by colleagues in Penn State which basically analyzed and proved that LIGO India will play a critical role in the next generation also. I have to tell you, for example, I have been focusing on gravitational waves detected on the Earth, which will be roughly in the hertz to kilohertz range. But just like electromagnetism is available in 2 decades of frequency, gravitational waves are also available in a full band. For example, there can be millihertz gravitational waves, nanohertz gravitational waves, and gravitational waves from the Big Bang, which will be in the attohertz range. People are talking about projects in these various frequency range. So, for example, in 2023, in the nanohertz range, detectors which are called pulsar timing arrays, they said that there is strong evidence for gravitational waves coming from supermassive black hole binaries. So, this is something where there is a kind of signature, not definitive, but evidence for that. 2035, a space detector which has been sort of funded called LISA is supposed to happen. The LISA mission was adopted in 2024. The construction is supposed to have begun in 2025, and in 2035 it will be sort of launched. There is something called the LISA consortium, in which you can participate even now if you are interested. And what is interesting is there will be multi-band gravity wave astronomy, because there are some sources like intermediate mass black holes which will be first seen in the LISA band and then a few years later seen in the LIGO band. So, all these are sort of exciting times which are supposed to really happen. We are already talking about the next generation detectors which will be 10 times more sensitive. This is the Cosmic Explorer in the US and the Einstein telescope in Europe. And these will detect almost all the CBC mergers in the visible universe. So, you can see that all binary neutron star coalescence, all binary black hole coalescence will be seen once these systems come into place. And therefore, we will begin from a situation where the sources were known, I call them known knowns. There are some sources which are known, but they are still unknown today. But our whole hope is that eventually we will see some exotic sources which I can call the unknown unknown. So, my last concluding session, the next generation network will have a transformative impact on the field of gravitational wave physics and astronomy, because it will lead to precision gravitational waves and multi-messenger astrophysics. There is tremendous discovery potential, because there will be cutting edge technology which will really happen. We will be able to say something about how stars and galaxies form, how we will observe the early movements of the universe, and instead of being only something about astronomy, we will say something about fundamental physics of QCD, neutron star matter, Hubble tension in cosmology, and something about the nature of dark matter and dark energy. So, the impact is much beyond gravitational wave astrophysics. It will touch fundamental physics, particle physics, nuclear physics, and therefore, the great sensitivity which we will have, it will lead to technological advances in aspects related to detection like electronics, material science, quantum computing, etc., etc. And therefore, you can see that it is not only about astronomy, but it is about fundamental physics. So, we are hearing very faint signals of gravitational waves, but they are whispers of a new revolution. So, to people like you who are just starting their career, I would just say, come decipher the universe using gravitational wave observation and multi-messenger astronomy. Each one of these blocks is a research problem to be investigated and research to be done. So, therefore, as you can see, it is an emerging area which will mature over the next decade, and therefore, a target of opportunity for all of you. Thank you for your attention. Just give me a moment to recover, and then I'll answer your question.